Graphics. In the beginning, it was punch cards, teletypes, and even oscilloscopes. Visual output is pretty much the only way we use computers. I mean, have you ever tried using one without a monitor?
What are you doing?
1977's Apple II is one simple example among many that shows how most computer graphics work. Within its memory map is a section of RAM dedicated to representing the screen's visual output, which is then taken and interpreted by the video output circuitry into something that we can see. Now, on this system, only one program would run at a time, meaning that it was no big deal to have a static area in memory to directly edit the pixels of the screen. Those were, of course, simpler times. While the race to have the best graphics heated up with the likes of game consoles from Nintendo and Sega who use special hardware features like sprites and tiles, along with the increasing popularity of personal computers and their technical improvements, the task always remained the same: calculate the color of each pixel to be sent out to the screen. The graphical capabilities of these systems only grew alongside the exponentially increasing computing power, and games quickly went from 2D with limited colors to 2D with more colors than the programmers knew what to do with, to 2.5D, wow, this might as well be 3D, to real 3D, actually that doesn't look so great, can we go back to 2D, to finally some good 3D. While Microsoft at this time was mostly concerned with building up Windows for business use, there were those inside the company that wanted to provide a better interface for programmers to develop games for the PC. Under the codename of the Manhattan Project, this group aimed to create a platform for developing games that would be better than those made for the Japanese consoles of the day. Because the only thing worse than imperialism is when foreign companies think they can just get away with selling their quality products without consequence. And so DirectX, a set of application programming interfaces, was released in 1995 in the Windows Game Software Development Kit. And from 1996 on, it not only began to come bundled inside Windows, but became the default graphics interface for the operating system, with even big titles like Doom 95 being ported from MS-DOS to DirectX that same year.
These games are getting really realistic.
240p Bill Gates, is that you? What are you doing here?
You might wonder what I'm doing here. Well, I'm getting kind of an inside look at some of these new games.
But is Windows 95 even a gaming platform?
First, Windows 95 is the game platform. Whether it's the best performance, the best setup, the best integration, with the toolkits we're putting together, we're going to make sure people are very focused on Windows 95.
But Bill, what about DOS and my DOS games?
DOS? It's been impossible to install the game, and nowhere near the graphics performance we're getting today with our DirectX APIs.
Okay, well thank you.
Don't interrupt me.
Bill Gates, you never cease to amaze the rock.
Over 25 years and several DirectX boxes later, and Windows is still using DirectX, a set of APIs which now includes Direct3D, Direct2D, Direct Compute, Xaudio 2, DirectX Ray Tracing, and many more components. Although the Direct2D and DirectWrite APIs, used by most Windows for 2D and text rendering, both run on top of the Direct3D API, meaning that for the hundreds of windows you may find rendering at any given time, the desktop window manager will compile these off-screen buffers into a single 3D environment to handle Z-ordering, window compositing, and create those sweet 3D effects. And now may be a good time to mention why they even call the OS Windows. That's because this is a window, but so is this standard UI button, and this label too, and this text area, and these scroll bars, and even these menu buttons on top here. Each of these elements is a window, meaning that it has its own window handle, render call, and I/O. Even your desktop is just a window, and these icons get this Windows. This certainly simplifies things for the programmer, who can just slap a couple of buttons and whatever else onto a base window and call it a day, without ever having to worry about the underlying logic of how these elements operate or are rendered. While the DirectX API was created as a game development SDK, most game developers nowadays choose to use an existing game engine that, like magic, simply handles 3D rendering without having to understand how any of it works. So how does it work? I'm not going to shy away from the technical descriptions or mathematics here, but if you'd like a refresh or a crash course in math, science, or data analysis, then you may want to check out today's sponsor, Brilliant, where you learn by doing through thousands of interactive lessons covering a whole range of topics from programming, probability, and large language models. Each lesson on Brilliant is tailor-made to develop your analytical thinking and improve your problem-solving skills through increasing your understanding of real-world topics, like through their Vectors course, which goes through both the fundamentals and dives into how the physics of motion translate to a digital environment. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/inkbox or click on the top link in the description. You'll also get 20% off an annual premium subscription. Again, that's brilliant.org/inkbox. The first step to creating a 3D rendering engine is to create a regular 2D window. This will eventually show the rendered output of the scene, and I can quickly create a simple blank window in the center of the screen here using C++. Windows allows you to create a window with or without a title bar. There are actually quite a few window options you can choose from, but for the aesthetic of it all, I'm foregoing any frills in favor of a simple, clean window. For my engine here today, I'm going to be using DirectX 11, not because it's the best version of DirectX, but because there are really no great tutorials for the newest version, DirectX 12. Next, I need to create a DirectX device, device context, swap chain, and depth buffer. The DirectX device is a representation of the system's graphics hardware. Beyond providing information about the graphics hardware and its supported features, it'll be used later to create resources like textures, buffers, shaders, and other objects. The device context is the interface through which the program interacts with the graphics hardware to perform rendering operations, and the swap chain is just a set of frame buffers. The buffer being displayed at any given point in time is known as the front buffer, while the others are known as the back buffers. The graphics device will do all the calculations for the next frame on the back buffer next in line, which will then swap out and become the front buffer. I'll be keeping it simple with just 2 buffers in the swap chain. The depth buffer is used to determine what pixels should be written to the back buffer. This will make a lot more sense later on, but as a simple example, let's say that in a 3D scene we find that there are 2 objects A and B. Let's say A is rendered first. After passing through the graphics pipeline, a set of fragments are created, which contain, among other things, the color of each pixel and the depth of that pixel, or how far away that pixel is from the camera. Let's assume all A's fragments are the same depth away from the camera. So these depth values are stored in the depth buffer, and the color data is then added to the back buffer. Now it's B's turn, but by checking the depth buffer, it's discovered that some overlapping fragments are further away from the camera than what is already there. So these pixels are not added to either the depth buffer or the back buffer. From here, I can create a couple more things, like the projection matrix that we'll come back to later. And after all this initialization, the swap chain is told to send the front buffer to the window that was created earlier. And now I can check the new Direct 3D output.
These games are getting really realistic.
And now is the part where in order to see anything, I have to start throwing some data down the gullet of the graphics pipeline. So let's understand each stage of a simple pipeline. In order to render a single triangle, each vertex's X, Y, and Z coordinate are needed. These can be stored in a vertex buffer in the graphics device's VRAM. After this, I can load in the shaders. A shader is a program used by the DirectX device to render the graphics data. These shaders are written beforehand in a language called high-level shader language, and at runtime are loaded from file and compiled by the program into a binary that can be passed on to the graphics device to be run by it later. The current program will use only 2 shaders in the graphics pipeline. A vertex shader, which processes each vertex into clip-space coordinates, that is, coordinates which will be used to determine what region of the scene is visible, and a pixel shader, which determines the output color of each fragment. Before starting the rendering process, I can update any data that the shader needs from the CPU. In this case, it's the world matrix, which represents where the vertices are located in world space, the view matrix, which represents what is being viewed in the scene, and the projection matrix, which maps the vertex position into the aforementioned clip space. For now, I'll assume that the world matrix is the identity matrix, meaning it can be ignored for a minute. And the projection matrix I already have from the initialization steps, but I still need the view matrix. This is what represents the camera of the scene and will determine what we're looking at in the final frame buffer. For now, I'll set this up to be a simple matrix defined with up as the positive y direction at coordinates 0, 0, -10. Then, taking the vertex data for the single triangle from before, it can be bound to the first stage in the graphics pipeline, the input assembler stage. Then, the rendering process can be kicked off by clearing the back buffer and depth buffer, then calling the device context drawIndex function, which will feed the prepared data into the rest of the pipeline for processing. The second stage passes each vertex through the previously loaded vertex shader, which determines where the triangle is located in clip space. And then, in the next stage, the pixel shader determines the color of each fragment in the triangle. At each stage, this isn't happening one vertex or one pixel at a time, but all the vertices and all the pixels at once, or at least as much as the device can handle at once. Part of what makes the GPU much faster than the CPU at rendering is because it's using single instruction multiple data instructions to process the same calculation in parallel on multiple data points. Between that and multi-threading to allow for different parts of the pipeline to run on different cores, then to a certain point, adding more triangles to the vertex buffer doesn't linearly increase the amount of time the GPU spends processing. After passing through those stages, the output fragments can be merged with the depth buffer and back buffer in the final output merger stage. The last step after that is swapping the back buffer to make it the front buffer, which will show the rendered scene in the window. Here, only a single triangle is being sent through the pipeline, but more data could continue to be thrown through until everything wanted in the scene has been rendered, and only after that showing the final output by swapping the buffers. Remember, it's all this processing to create a single frame displayed for at best 1/60th of a second. That's quite a process, but it doesn't really get any harder than that. After all, if the pipeline can render a single triangle, then why not two at once to make a square? In this case, we could use two independent triangles with 3 points each, but that's a waste of memory since two of these new vertices are the same as in the old triangle. So it's better to use an index buffer that keeps track of which vertices are used in each triangle, making the vertex buffer a list of points, and the index buffer a list of which 3 points make up each triangle. Both the vertex and index buffers are stored in VRAM, where they can be bound to the input assembling stage of the pipeline. Then, after calling the aptly named drawIndex function, will be processed by these shaders and merged into the output. Now, instead of merely having color output for the rendered polygons, what if some portion of an image was displayed on the surface instead? This would be known as the triangle's texture, and it can be stored as a TGA file, a raster graphics format used for storing images with a specific number of bits per pixel. On startup, the texture can be loaded from file and saved as a shader resource in the device's VRAM. But now let's look at what's actually going on in these shaders. First, the vertex shader has a few global variables. These are the variables I mentioned before get set by the CPU before the render process is started. Then there are two structures. These represent the vertex shader's input, being a float 4 for the vertex's position in space and a float 2 for the texture coordinates. We'll come back to this in a second. The output of the vertex shader function below will become the input of the pixel shader, which will be the clip space coordinates and the same texture coordinates. Down here is the actual meat of the shader program, and you can see that all the vertex shader does is calculate the vertex's clip space coordinates from the input and pass that along with the texture coordinates out to the pixel shader. For texture mapping, each vertex in the polygon has an associated texture coordinate u and v. Each is a float and range from 0 to 1. A u value of 0 is the leftmost part of the image, and a value of 1 is the rightmost part. Same with v, but vertically. In this way, the texture can be any shape or size, and the uv coordinates will still represent the same proportional location on the image. With 3 different points overlaid on this image, it's easy to see how this will be mapped onto a triangle, and we can check out the pixel shader to see that it simply runs the sample function on the associated shader texture, which will return the color for the relevant fragment from that texture. Stick 2 triangles together and the whole image can easily be displayed if the UV coordinates are correct. Now, because all this is happening in 3D space, some spin can be put on these 2D triangles that we've created by rotating the world matrix by an increasing angle. So we can clearly see that this is really happening in 3D, and while you don't have to have a super robust knowledge of how matrices work, you should at least be aware that the commutative property does not apply here. So matrix A times matrix B does not always equal matrix B times matrix A, which gives us a proper order to multiplying when we are applying transformations to the world matrix, usually always scaling and rotating before applying any translations. Another improvement that can be made in the shader is to calculate the current light level on the object to add shadows to different parts of the model. So before rendering, the CPU can provide the light direction and color to the new pixel shader, and then for each vertex I need the x, y, and z coordinates, the u and v coordinates, and now the normal direction, which means what direction is at a right angle going directly away from the vertex. So for each triangle in a simple model like this, they all have the same normal direction, but that isn't necessarily the case in a more complex model. In the new light vertex shader, I've changed the input and output structures and added some additional calculations to determine the normal direction of the vertex in terms of clip space coordinates. Then in the pixel shader, the light direction can be used to calculate the amount of light hitting the object. If the surface is directly facing the light direction, then it'll appear at 100% brightness, and if it's facing the opposite of the normal direction, it'll be 100% black. The diffuse color simply means what color should be reflected from the light source. For white, it'll bounce back everything. If it's a pure red light source, then only red light will bounce off the object. If we don't want polygons facing completely away from the light source to be completely black, then we can add some ambient light with some simple math. Then the sample color of the texture is multiplied with the light color to produce the final output color. In this example, the source of light is directly coming from the camera's location, so the polygon becomes darker as it rotates away. When I set up the Direct3D device, I also made sure that non-front-facing triangles were not drawn to the scene, so we won't see anything from the back until it rotates back around into view once more. So if one triangle can be drawn, then a whole set of triangles that make up a model can be drawn too. And a standard OBJ file contains all the data that we need in plain text, just not the format that our shader is used to. Now I've been reading a really helpful guide on DirectX 11 programming from a certain rastertech.com, and he's provided a simple program that will convert standard OBJ models into a simple list of vertices that are compatible with our shaders. So I can use a 3D modeling application like Blender to make a model, or download a model from online, throw it through our program to get the X, Y, Z, UV, and normals that we need for each vertex, and then when the program loads, store that model's data in a vertex and index buffer in VRAM. Now the model can be rendered a single time, or since it's just in VRAM already, it can be re-rendered in the scene as many times as needed, each time performing a different transformation on the object. So for any game I design, I only have to load in each model and texture a single time into VRAM, and then they can be re-rendered on demand. So remember back to when the camera was set up to create the view matrix? It was placed at position 0, 0, -10. So with a little configuring to grab the keyboard input from the window, I've managed to allow the camera position to change when the user presses WASD. And even just this is really exciting. And then with a little more input to get the change in position of the mouse, I can look around the environment. Not really much to see anyways, but oh, okay here. So I'm pressing W, but I'm not walking forward, but I am walking north. So for W to equal move the direction the camera is facing, I just need to get the X and Y component of the distance to travel based on the camera's current angle, or in this case, X and Z since Y is up. And look at that, it's working now. And this is really amazing how cool it is. Just moving back and forth in a 3D environment built from the ground up. I mean, there isn't any ground right now, but I'll fix that in a minute. At this point, I can load in basically any arbitrary 3D model I find online and give it any texture. So there's really only one thing left to do: make a game. Except that any good game needs a good UI, which usually incorporates some kind of heads-up display. Now, I can't tell you why, but I had a whole lot of trouble trying to get 2D rendering to work. The way it's supposed to work is that instead of the projection matrix, I used the orthogonal matrix created in the beginning alongside the projection matrix to render things in a static position on the screen. I just couldn't get it to work for me, so I had to develop something to work around that. Remember that for each object rendered to the scene, 3 matrices are provided. The object's world matrix, representing its scaling, rotation, and position in the world, the view matrix, representing the camera's view of the world, and the projection matrix, which gives us a field of view. So here you can see my cheese model that I've imported here. I've tried to calculate a world matrix that will move my cheese in line with the camera. Let's give it a quick test here, and that seems pretty close, but looks like it's a bit off. So if I want an object to appear static relative to the camera, that's like saying that I want the camera's world transformations to be cancelled out, so that the object appears at 0, 0, 0, or wherever I want it to appear relative to the camera. Let's think back to linear algebra, or if you've never learned linear algebra, think back to after you watched this section. To cancel out the camera's transformations that are in its view matrix, I just have to get the inverse of that matrix, because when these are multiplied in the shader, that results in the identity matrix, the matrix equivalent of a 1. It's like saying n multiplied by inverse n equals 1. I can't divide by the matrix here because, as we all remember, there is no such thing as matrix division. And then if another transformation is made on top of that inverse view matrix, then that will be carried out relative to the camera. So I should be able to see the cheese directly in front of the camera at all times. But we do see that this cheese is literally just hovering in front of my face in 3D space. However, if we don't want this to be affected by the other polygons in the scene, then we can simply temporarily turn depth testing off, which will just skip checking our depth buffer from before and simply add everything straight to the back buffer, and then turn it back on after our cheese is rendered. And as the kids say, that's pretty cheddar. Now, it wouldn't be a HUD without text, but I don't want to include a 3D model for every single letter, number, and symbol. That would be ridiculous. Instead, I can include a single texture that represents ASCII from 0 to 255, though I'm only going to add the basic letters and numbers that I need right now. Then I can use a model made of 2 simple triangles that will make up a square. Normally, when we take the model's data and create a resource in VRAM, we define it as static, meaning that I'm not going to touch it ever again, and even if I wanted to, I can't. But for this model, I want to dynamically change the UV coordinates of it so that I can display different parts of the texture. It isn't too different to set up the model in this way, but it should be noted that static buffers will be more efficient, so you should only make the buffers dynamic when necessary. I've built up another class that contains a vector of strings with certain screen positions, sizes, and colors. For each character in each string, the model's UV coordinates are changed to match the ASCII character's position in the texture, along with changing the location on screen that the character will be rendered at. I won't use the light shaders either. I'm going to create a new shader that will use the color passed along from the CPU to determine the output color of the text. And I've also made sure to enable alpha blending, so that I'm not looking at a white block around the text. So let's test this out. That's not what that's supposed to say. Hang on 1 second here. And here we go again. What does that say? Subscribe? Oh man, who put that there? This is so embarrassing. Anyways, let me quickly create some ground here so we're not just staring down at the endless void. I could use just a single large cube, but that would stretch the whole texture over the entire area. Not very nice looking. Rather, by breaking it up into 100 smaller cubes, the texture looks much better. Then, to cover the vast expanse of space outside the island created here, I can create a simple skybox by sticking 6 different squares all around to create a kind of inverse cube, and that looks absolutely brilliant. I've also added a subtle spin on it all just so that it has a bit of movement, and that is much better than looking out at the void. At this point, the 3D rendering engine portion of everything is more or less complete, so it's about time I start building out the actual game. There isn't a more traditional game I'd like to make in a 3D engine than a 3D shooter. But I don't just want to use a regular gun. Boring. I'd really like to make it almost like a typing game, like Typing of the Dead, except without the vocabulary. Essentially, I'm going to turn the keyboard into a machine gun, where each key press equals 1 shot. Step 1 is to add a keyboard model that I've subtly modified in Blender to the HUD, along with adding a crosshair, which is just the plus character from the font. Then I'll need to add in a 3D model for every letter, number, and symbol into the game. When that letter is pressed, then bang, it'll spawn into the world. Over there, I guess. Oh, I forgot to add their coordinates relative to the player. How about now? And alright, this is pretty cool. It's a bit scuffed when I go up high, but you don't know how long it actually took me to get it like this. 2 dimensions? Easy. 3 dimensions? Yeah, it's a bit harder. But after this, it isn't much trouble to give these letters some speed and send them out flying into the world. And yeah, that's actually pretty fun. But there is one important improvement I forgot to make with the engine, and that is culling. Currently, I'm sending every single object in the scene into the pipeline to be rendered every single frame. To give it a little push here, I've increased the size of the island and broken it into 50 by 50 cubes underneath. Now that's over 2,500 objects in total. And for just the cubes, we can calculate that at 12 triangles per cube, that's 36 vertices each. Then at 60 frames per second, the vertex shader alone is being run 5.4 million times per second. Again, just for the floor. Granted, a lot of that is happening in parallel, but our game will be exponentially more efficient if we only send the objects that the camera is looking at into the graphics pipeline. That area is called the view frustum, and it doesn't extend infinitely outward, so the 6 planes that make up the frustum can easily be calculated. Then, before rendering a model, a sphere of some scaled size at the model's center point can be tested to see if it lies within the view frustum. If so, the model can be sent on to the pipeline. Otherwise, no need to bother as it won't be seen anyways. You can see that these calculations are significantly reducing the amount of work needed to be done by the graphics device, which will be a huge help, especially as I'm about to design the most complex model in the game so far. Here in the back, I've generated some cheese, and in this game you're going to be defending your cheese against the enemies. So let me open up Blender to design those enemies here. I'll create a sphere, and then I'll copy in a fedora and give him some sunglasses, and there we go. That's much cooler than my original idea of just a regular ball.
These games are getting really realistic.
In terms of texturing the model how I'd like, I can come to the shading tab and add an image texture, connecting that node to the color. Then in the UV editing tab, I can select the model and unwrap the polygons with Smart UV projection. This places each triangle in a unique position somewhere in this texture. That allows me to be able to select certain polygons. Then in the texture paint tab, come fill those sections with the color I want. The model can be exported as an OBJ, and for the texture, I can take this and create 7 more copies in different colors. These different colors will represent the different amounts of health that the enemy has. In a tower defense fashion, each wave will have increasingly many enemies with more and more health. I've started programming a simple AI for them, where after they spawn, they'll feel pulled toward a particular piece of cheese. Then once they arrive, they'll pick it up and run back with it. Where are they running back to? Why, it's their spaceship, of course. Each wave will drop the enemies out of the ship, and it's the player's job to hold them off and defend their cheese as long as they can, and believe me, it can get pretty intense. But the machine gun keyboard is super fun to use to just spray letters into the enemy. And after the final polishing of it all, the title screen, the settings, the playtesting from those in the Discord, it did wind up looking more or less like a basic game someone could make in any generic game engine. And that makes me super happy because all of this, the entire world that I'm seeing, was created from nothing. And the entire compiled program comes in at just 1.24 megabytes. Knowing how a 3D engine works has given me such an appreciation for the millions upon billions of calculations happening every second to create such beautiful worlds. And there's really only one thing I want to say.
The letter of the day is pain. I'll make you eat those words. Spell you later.
Thank you once again to Brilliant. Check them out down below, and tune in next time where I find out what my Raspberry Pi was doing the whole time, and that's not a joke.